Hello, everyone. We'll get started here in a second. Okay, it's now 11:01, so we'll go ahead and get started. This is a seminar for the Propulsion, Power, and Thermal Systems Laboratory here at Tennessee Tech University. I'm Rory Roberts, an associate professor here at Tennessee Tech in Mechanical Engineering. And this project will be presented by Jimmy Meacham, also goes by Will, so you may have saw that in the invite. This is part of his master's work, looking at liquid natural gas for aviation, and particularly how it can be utilized to cool electric motors by thermal management, and on top of that, increase capability in electric machines. As part of this seminar, we plan on doing these once a month with the students in the lab, so they get an opportunity to present their work and also get feedback from others. And so if you don't have my email and you were forwarded this and you want to be on the contact list, please just email me and I'll add you to it so that you can be invited each month. And feel free to distribute these invites, and these will also be recorded and uploaded to the same page that you found the link to this Teams. And so with that, I'm also please can save questions to the end. Will be about 20, maybe 25 minutes presentation, and we'll have questions at the end. And just to go on, this project was sponsored by RPE, but Jimmy will talk about it. It's led by Hypertech Research with Ohio State, Raytheon, Boeing, and Aerospace Systems Director, and Tennessee Tech participating. With that, I'll hand it over to you.
Thank you, Dr. Roberts, and thank you everyone that has come to listen to this presentation. I'm really excited to be presenting this work and also the progress and results of this. And without further ado, let's get into it. So my project is based on doing a simulation of the analysis of the thermal management system for electric aircraft using liquid natural gas as a coolant. And Dr. Roberts already explained this first slide. So what is the project purpose? The primary purpose of this project is to verify the viability of using liquid natural gas as in a proposed thermal management system for electric aircraft, and if it is viable, determine the performance, if the performance reaches the goals of higher power density and higher efficiency of the electrical systems. So let's look at some of the possible benefits that this type of system would provide. First, we have reduction in greenhouse gases by using renewable liquid natural gas as the coolant and energy source for the turbo generator. This reduction can be had by obtaining Bio-LNG from biomass collection facilities. Another benefit is the reduction of methane emission to the environment, as methane is more harmful than carbon dioxide. Liquid natural gas also burns cleaner than normal jet fuels and is easily accessible from many different sources. Next, the weight of the plane can be reduced by having a combined thermal system and fuel system. This reduces the need for an independent cooling system for all the electrical loads in the plane. Another benefit is the addition of low resistance materials in the motor, cryo cables, and generator. When these systems are cooled to 120 Kelvin or below, they have an electrical resistance that is equal to 1/3 of room temperature resistance. This leads to an increase in power density and higher electrical efficiencies due to lower power losses from the resistance. The last benefit is potentially lower risk and more viable systems by liquid natural gas than that of superconducting systems. There's no use of exotic materials or hydrogen, reducing the cost and weight compared to those superconducting systems. And below is a proposed system that we will look further into later. First, let's look at this graph, or this table. This was provided by Hypertech Research, and it kind of looks at the different types of cooling methods for the motors. And in the diagram, we can see that as we give more cooling to these motors, we get higher power densities. And the focus of this project was the proposed cryo system, and being able to have the lower electrical resistances just gives us more higher power density in these electric motors, motor drives, and in the thermal system. And we don't have to go through the higher risk of having a superconducting system. Next, this is the model that was used, or this diagram was used as a baseline for the simulation. Simulink and Matlab were used to perform the transient analysis of this system, and each component modeled in Matlab and Simulink was also tested using a steady state solver to verify that the equations gave correct outputs. Using Matlab and Simulink allows for the user to easily change many different inputs and other parameters quickly, and being able to analyze the given data quickly as well. The diagram below shows what we modeled. Beginning with the left, we see the Bio-LNG tank, and following the arrows, we have the LNG pump, electric motors, cryo cables, generator, vehicle thermal loads, mixing chamber, and compressor. And then after that, we have the control valves for the turbo generator and also an overpressure valve. The turbo generator was not included in this simulation, and this will be discussed further. But for now, we have a mass flow rate demand to model to represent the turbo generator. Next, we're going to look at the system P&ID. So this is a piping and instrumentation diagram that was created to allow for further analysis of the failure modes that could occur with a practical implementation of this system. As each component was analyzed for its failure modes, we were able to optimize the operational parameters that would help prevent some of these failure modes. This also allows for the development of a failure modes and effects analysis. And this would give us even more merit to the possibility of the system being built, as each component would have its own risk evaluated and graded. The grade of risk would determine the steps needed to be taken to ensure that it does not occur. This piping and instrumentation diagram is subject to change as more failure modes are detected. Next, we're going to look into some of the more important portions of this model, beginning with the Bio-LNG tank. This tank is going to hold all the fuel for this entire flight. A few assumptions are made to ensure the proper behavior of this tank. First, we assume that the properties and everything about the liquid is based on a saturated fluid and vapor. But notice that the saturated vapor and liquid are perfectly separated during the entire flight. The pressure inside the tank is controlled by two methods. One is a pressure release valve and one is a heating coil. If the pressure in the tank becomes too high, the pressure is released, or the saturated vapor is released into a mixing chamber deeper in the system. And if the pressure gets too low, the heating coil will turn on and vaporize some of the liquid to cause the pressure to go up inside the tank. The exiting flow of the tank is assumed to be a saturated liquid, as boiling this liquid is the primary cooling method that absorbs the heat generated by the electrical systems. A sizing routine for the tank was included to ensure that the heat transfer to the environment was analyzed as well. And this is based on some specified thickness and conductivity of insulation. So next we're going to look at the nodal heat exchangers. Each of the components listed, the cryomotor, generator, cryocable, vehicle thermals, were all developed using the same method of a tubular nodal heat exchanger. An assumption that was used was that the heat is perfectly transmitted into the flow, and there is no external heat transfer from the environment. And another assumption is that the saturated mixtures are perfectly mixed. And each of these heat exchangers were designed to handle subcooled liquid, superheated vapor, and saturated mixtures or saturated flows. And the correlations for each, the superheated or the single phase and the mixtures were developed, and as you can see below. And each node of these heat exchangers has different geometry, and these can be quickly configured to allow for more accurate analysis of each node. So, getting more into the actual flight and simulated flight profile. Shown here is a commercial flight profile for a Boeing 737 class proposed electric aircraft. And as we can see in this diagram, we have three distinct regimes of the flight: takeoff, cruise, and emergency takeoff. As these are the most important parts, excuse me, and we will be able to see how this system reacts to, say, the emergency takeoff whenever we have extremely fast and high loads, and also can see the cruise parameters to see what we can work with during the cruise. And the power demand given is based on a percentage, where during takeoff we have a peak of around anywhere from 28 to 30 megawatts. We can determine the heat generation for each component and the flow needed for the power generation during this entire flight profile. So using that commercial flight profile and also a few efficiencies, we were able to determine a mass flow rate demand and a heat generation demand during the flight, with the electric motors and generator having an assumed efficiency of 99% and the cryo cables having a 99.9% efficiency. And this assumption is based on the reduced electrical resistance provided by cooling the components to the cryogenic temperatures. The system will have between 12 to 14 motors in an array, and each motor will have, in this simulation, each motor has a perfectly equal flow and equalized heat generation, and we will be analyzing all of them. So, looking at the actual simulation parameters for this model, beginning with the tank, we have it at 56 kilopascals and 104.5 Kelvin, a saturated mixture with saturated liquid coming out of the tank and being pumped up to a subcooled liquid that will go into the motor and begin boiling or vaporizing to be able to take away the heat generated. And then from there, the flow goes to the cryo cables, still vaporizing, and the generator still vaporizing before it makes it to the vehicle thermal loads, which will intend with a 200 kilowatt Q generation. It is needed that the flow be fully vaporized before it reaches a compressor, and then we have some pressure goals for the mixing chamber and for the turbo generator compressor. Looking more at direct goals of this system, one is the motor cooling. And this is the primary objective, is to ensure that the motor has enough cooling to maintain it at between 110 to 125 Kelvin, so we can take benefit of the 1/3 resistance. And also we want to make sure that the flow itself is vaporizing in the motor. Next goal is to ensure that the flow is fully vaporized whenever it reaches the compressor. So we added a generic heat load right here, and this generic heat load can be changed in the future for future analysis to modeled after more realistic heat gens inside of the plane. Next, we're going to look at the compressor. The compressor's job is to maintain the fuel demand that is demanded from the turbo generator and also ensure that the pressure for that fuel is maintained at, a pressure sufficient enough for the whole flight. First, we're going to look at these motor results. Shown in the top right graph is the average temperature of the flight during the average temperature of the motor during the entire flight profile. During cruise, we have a temperature of 117.1 Kelvin, and we notice that there is a peak temperature, and this is during the emergency takeoff with a peak temperature and pressure of 122 Kelvin and 180.8 kilopascals, with this surge only lasting approximately 8 seconds. And this is understandable as the rapid increase in demand and just surges throughout the system. And it soon becomes leveled back out to acceptable levels. In the bottom right is the flow temperature exiting the motor. And this shows that as the pressure changes, the temperature of the flow for the saturation temperature will also change. And throughout the entire flight profile, we notice that the temperature of the flow is sufficiently low to cool it to the temperatures we desire for a lower electrical resistance. In the bottom left, we see that the quality of each node exiting, or the quality of the flow exiting each node is between 1 and 0, and this demonstrates that each of the nodes has boiling occurring in it to allow for the higher rates of heat transfer from the vaporization of the liquid natural gas. Next, we're going to look at the vehicle thermal results. During the cruise, the max temperature is 267.5 Kelvin with a 200 kilowatt load. And this relieves some room for further cooling if any other systems need the cooling. And the peak temperature during the emergency takeoff is 302 Kelvin, and this quickly goes back down due to the higher flow rates demanded by the system. And this sudden drop may need to be looked at further, as we want to ensure that certain systems aren't cooled excessively. And shown on the left is the graph of the quality exiting each node of the vehicle thermals. And we notice that the last two nodes, nodes 4 and 5, show that it is above 1, or at 1 or above 1, so we know that the flow is fully vaporized during the entire flight. Lastly, we have the compressor thermal results, or compressor results. Shown in the bottom left is a comparison of the demanded flow rate of the turbo generator and the provided flow rate from the compressor. Notice that we only really see one line because they are stacked, with a little bit of variance in the flow at certain step points in the system. But this meets the requirements of the turbo generator and does not deprive it of the fuel needed to generate the power. And the pressure demand for this system was kept at 20 bar for simplification purposes, and changing the pressure demand will be further analyzed in future analysis. But in this case, the pressure is kept sufficiently high, around a pressure ratio of 20, to ensure that the fuel is going into the motor throughout the entire flight. And this pressure was captured by a high pressure plenum analysis. Another thing that will be looked into in future analysis is the inertia of the shaft for the compressor and other dynamics of the valves in the system. So the system model has shown that the use of liquid natural gas as the coolant and fuel for the system meets both the thermal and fuel demands for the entire flight. We're able to see the lower benefits in resistance in multiple components due to the cryogenic temperatures of the heat exchangers, especially the motors. The vehicle thermal load ensured that the flow to the compressor was fully vaporized and the exiting flow is not at an excessive temperature and may be used for other systems within an aircraft. The compressor model also ensured that the pressure and mass flow rate demand for the turbo generator were met throughout the entire flight. Like I said before, that we do definitely have some future work, but this model has been made and gives us the groundwork for changing certain parameters to get more accurate results. And some of the further work would include modeling a full array of motors with differential thrust profiles to see how the individual lines and motors react to different loads at different times. Excuse me. And then at the addition of more accurate heat loads, such as vehicle thermals and just other heat loads would be beneficial to the accuracy. Another thing is adding data from other teams to get more accurate geometries and heat transfer coefficients due from their testing. And implement non-constant efficiencies. So the efficiencies for the heat exchangers were assumed constant, but as the temperature would change, we know that this would also change. So adding that kind of correlation would be further down the road. And then combining this model with a turbo generator or solid oxide fuel cell hybrid model to get an accurate depiction of a demand for mass flow rate would be very good. It's going to be a future work. And that's it. Is there any questions? And thank you for your time and any questions.